lunchtime lecture. And my notes have just disappeared. Bear with me a second. Today we welcome Zakhele Nkosi to give us a presentation. Zakhele completed his studies at the University of Pretoria. His M.Sc dissertation, which dealt with mineral carbonation using platinum mining derived tailings, earned the 2019 John Handley Award by the GSSA. He is currently pursuing his PhD at the University of Johannesburg under the supervision of Professors Altermann and Viljoen. The research is still on mineral carbonation. However, this time he has moved away from platinum tailings to kimberlite tailings, which in my opinion is always a good thing to do at any time. Zakhele is currently serving as a member of the academic staff at the University of Pretoria and has a core teaching focus on applied mineralogy, paleontology, paleoclimatology, and geoethics. Most of his time is devoted to teaching first and second years, but he is also supervising 2 honor students as well as an M.Sc student. So Zakhele, we look forward to hearing from you on negative GHG emissions. Can the earth sciences come to the rescue?
Thank you so much. Yeah, I'd like to greet everyone and firstly thank everyone for coming and joining us today. I hope you can hear me clearly. And also thank the Geological Society of South Africa for organizing this. So even though we might be so far apart, I think also we've got friends who are joining across the ocean. It really is quite nice to still feel connected with everyone. I will jump right ahead. So as correctly attributed, this talk today is related to my PhD research and master's research, and hopefully will be continued research even after my PhD, as you will hopefully see later today. So the topic is negative greenhouse gas emissions. Can the earth sciences come to the rescue? And so I've approached this in 2 or in 3 themes, or there'll be 3 riding themes. The first one is just, housekeeping, which is the premise of this lecture. I mean, I always believe in having a good premise so we at the very least, we can all relatively have the same page. And if we are not on the same page, one can know that we are not on the same page and that everything else that follows is based on the specific premise. So I always like to start with the foundation. And then I'll move on to the Earth systems and climate change, looking at and just giving a brief overview of Earth systems and climate change and how they interact. A bit of a refresher course, in some cases for some people, it would be an introduction, as it were, around Earth systems and how they interact with the climate over long periods of time. And finally, enter into the meat of this entire lecture, which is negative greenhouse gas emissions, discussing or going deeply within it and indicate or elaborating what exactly is imagined by the idea of greenhouse gas emissions. So let me jump into my first theme. So the first part of my theme is, what did I have for breakfast? So that's the first component of my lecture, and the idea here is it's really inspired by a paper that I once read when I was in my undergraduate, and it really inspired me to think radically as a scientist, and more specifically politically as a scientist. And the idea is the paper by Carol Hanisch, which says the personal is the political. And the idea behind this was a paper written during the second wave of feminist movement in the US in 1970. It was edited by her colleagues. And one of the most interesting things about this paper that she does, she really breaks this veil between what one does personally and what is considered to be political, and it really got me thinking at a very young age, or even in my undergraduate, thinking that for the longest time, I was always assumed that everything we do, however trivial it may seem, is actually very much political. So even what you have for breakfast is actually a political choice. You need only to travel to Mozambique, where you get there and you order breakfast and you ask them, oh, can I have an English breakfast? And everyone looks at you, weirdly, because an English breakfast is considerably, something foreign for them. And in fact, unknown. And you realize that there is a whole history around so-called English breakfast. Of course, South Africa was colonized, or was an imperial colony of the UK. Most of the cultural practices we have here are actually deeply drawn from there. So even a trivial thing such as having breakfast was informed by that political history. Even cereal, for that matter, because of the resurgence of the American imperialism having basically taken over the world, cereal has become a staple for many people in terms of their breakfast, cereal and coffee. So it's, again, it may seem like a trivial thing, but it really is also a political act, because that informs your position, or is informed by your position in society. What you have for breakfast is informed by your economic and political position in society, And so the idea that we are indeed always bound by historical, geographical, and lived experiences is important to me as a scientist, because as a scientist, I always believe that my politics must always come in when I do my science. And most people assume that real scientists must be apolitical, it must be objective. And I actually call, bullshit, because I think actually this is perhaps one of the biggest problems about science today, is that we think that it's separated from politics. And in fact, this is why certain politicians can hijack scientific discussion or discourse and basically make it their own. Why? Because scientists refuse to take political positions in certain things, or even for that matter, admit their own political biases. And I always start this lecture with my first years when I do an introduction around paleontology and we're looking at evolution. And one of the core things I teach them, or at least try and have a conversation around, is the idea that, as it were, if you look at the history of science, at one point, it was considered to a scientific fact that Black people are not human beings. They are subhuman. And this you can find in any scientific journal, that currently exists or preserved somewhere. And this was science, prevailing science. And there was science at one point that suggested what women are hysterical if they, even for that matter, decided to backchat or point out their own point of views in the family home. They considered to be hysterical and needed to be taken to a doctor. This was at one point science. And so we need to become actually political as scientists, so that we interrogate our own subjectivity and interrogate the work that we do as also political work, because it informs the politics of the day. And such the personal is indeed the political. So therefore, I'm of the school of thought that scientists need to be more philosophical first, or need to have a deep philosophical grounding or political grounding in order to become the better or the best type of scientist out there. And to actually even fight against what is now also on the rise, scientific dogma. And I think a lot of scientists have become dogmatic themselves, which is ironic, because science is considered to be apolitical, but it's because we've rejected our subjectivity. We've assumed that we are objective. We think we are apolitical, and I disagree with that. And so my politics emanate from a perspective of that being a young Black male based in South Africa with a specific history. I am privileged as a male, and I enjoy certain privileges, and of course, don't enjoy certain privileges considering of our social structure. And that has shaped my worldview. As a result, I tend to reject a lot of capitalist ideas, and I think the world needs to move towards less of a capitalist and consumerist idea, and we need to embrace the philosophical idea of Ubuntu. These are my politics that I enter a classroom with, I enter the lab with, and I bring them into this space. And every time I work, it is with this idea. So I believe in essentially a democratized society that does away with poverty, does away with gender discrimination, and many other types of discrimination. And it informs every aspect of who I am. And I hope that will also come through as I give this lecture. The second premise is more around the sciences, which is the Earth flat? And, of course, for most of us in this digital or virtual lecture room, we may think that this is an obvious question, this is, it doesn't even need answering. But I actually always ask, even myself and my students, everything that we assume is a given. We must always also be very critical of it. Is it really obvious that the Earth is not flat? And again, this does pull a little bit from the previous premise around one's politics, but now it goes down to the nitty-gritty of science, because for the most of us, we assume that this is the case because, well, we've learned it. But if you actually looked at what are the key attributes that could tell us what the Earth, or how one knows that the Earth is flat, some of it actually do emanate from your privilege. So if you've traveled across the world, I've had the privilege to travel to the USA and other parts of the world outside of my continent. And so in that moment, I'm able to observe the sun setting or the sun rising, the sun setting at 10 p.m. or for that matter, rising at a specific time. And then if I call my mom, I realize it's dark at her side of the world. That tells me relatively that, oh, the Earth is actually not flat. It's a geoid. Or for that matter, if you've had the privilege of even going to the ocean, you can see the horizon over there. And if you've had the even better privilege of getting into a boat and sailing with that boat and realizing that the horizon never ever gets to, or you never get to the horizon, that already should tell you that the Earth is most probably not flat, because you never get to fall off the edge of the Earth. So the point here is we have to interrogate even the ideas that we think are facts, that we think we understand about the world, and interrogate why we think that's the case. Because it's important to establish or to always be critical even of what we think is fact. Because at one point, what is a fact today used to be fiction. So the fact that the Earth, or we understand that the Earth is a geoid or is round, was fiction at one point, because science hadn't advanced to that level. There's so many aspects of what we take for granted. Plate tectonics was at one point considered to be a fictional thing. And today, any geology students will tell you that plate tectonics is a fact, and we know this because of this and this and this. But at one point, before science made that advancement, we assumed that it was fiction. So it's important to always be critical of even what we think we understand. And finally, climate change or climate crisis. So that's a question we have. It's one that is slightly semantic, but I think it's even a more critical question. So the entire presentation today is based around, or is centered around, this issue or discussion of climate change. But there's been rhetoric these days of asking that we no longer call it climate change, but rather call it climate crisis. But I'll even take it a step back and say, is climate change really happening? And it's a question we need to ask, which is, based on my previous premise. And I interrogated this question when I was in my undergraduate, when one of our professors, he was the HOD at the time, he basically, told us that the idea of climate change being something for us to fret over is actually nonsense, And his argument was quite simple. Says the Earth has had a very long and somewhat tumultuous and dynamic climate history, and often controlled by variables that in some parts, or in most cases, are very hard to understand, And so the climate change that we see today, first of all, is from a perspective of a human lifespan, or even several human lifespans, but still in the relative context of geology, it is a bleep. And he argued that if we then want to base our entire idea that the climate is changing, of course the climate is changing. It has been changing for billions of years, and it will continue to change for as long as the Earth is rotating around the sun. And so he argued that it is an irrelevant thing for us to be concerned about the climate change, because most of the variables are outside of our control. And at one point, this was a thesis that I held dear to my heart. I assumed everyone was just crazy people talking nonsense and, telling us that the climate is changing and it will obviously result into environmental disasters. But even that has changed over time, and you'll see why I say that. But we also have to challenge what we understand about the concept of climate change. Some people say we need to consider it as a crisis. But a crisis is only a crisis when we are personally affected. And I think the current events are an indicator now, because scientists have been telling us about potential dangers of what we're facing now, long time ago, but no one cared about it. But now that it is an actual crisis, we are suddenly faced with the reality of it. And so for the most part, climate change is not a crisis for most of us, because as George Gershwin says, for most of us, and especially those who happen to be privileged, it's still summertime and living is easy, the fish are jumping, cotton is high, your dad is rich and your mama's good looking. So essentially it's still good and well, and for most of us, our reality, the climate changing is not a crisis at the immediate time. But that will change, and my presentation will hopefully demonstrate why that's the case and why we need to actually move towards seeing it as a potential crisis and what are the possible things that we can do to avert it. So, to my second theme, Earth systems and climate change. I'm going to just briefly do a bit of an introduction of how the Earth operates. And again, I'm by no means an expert in this. This requires people who've studied various components. In fact, this is precisely what is problematic about understanding a climate, because it's so intertwined with so many systems that are studied in silos by different people, from geobiologists to even marine biologists, all the way to paleoclimatologists, to paleontologists. And so for all of these people, most of the time, to come into the room and really talk about everything that they've studied is really difficult, because all of them also study different parts of the Earth's history. Earth's history is over 4.5 billion years old. And that's a lot of history. And most of us just carve out pieces out of that and focus on that particular niche of the time, or even subject to focus on. And so the climate change or the climate changing over time is an effect of the interaction of the various systems that are interacting with one another. And the most classical systems are the different spheres that make up the Earth: the atmosphere, the biosphere, geosphere, and now the hydrosphere. And these are the different spheres that are interacting with one another, or we can consider them to be reservoirs. Atmosphere, reservoir, a system or mixture of gases. The biosphere includes you and I, and the plants, animals, and everything else that is considered to be living. The geosphere is everything that is rocks all the way to the core of the Earth. And finally, the hydrosphere is everything that is water, and part of that water system does, in some cases, end up in the atmosphere. And there's a constant interaction and movement of matter between all these four different spheres. But within that, there is other systems that are at play. Plate tectonics is one of them, the sun's radiation, our orbit around the sun, and indeed sometimes random events like meteorite impacts. All of these systems, you can imagine, are a melting pot of systems that are constantly interacting with one another, and as a result, drive our climate. And that can change over time. If you suddenly have a drop in temperature, you will have a high amount of precipitation in the form of snow, and that results in most of our precipitation accumulating as ice, and that then results into a cascading effect of ice reflecting out most of the sun's radiation, causing the Earth to cool down even further. And that creates a much more colder, or so-called cold house effect. And so you can imagine many other scenarios of all these complex systems interacting with one another. And as a result, they will produce a net effect in which we can observe as the climate changing. So we can, all the way from a volcano erupting, that can and may result in more CO2 in the atmosphere and many other types of gases, which may force the climate to a specific direction. The erosion of the mountains in it of itself can reduce the amount of CO2 in the atmosphere and trap it in other so-called carbonate or storage rocks or carbonate rocks, which then bury the CO2 from the atmosphere, and that will result into a net reduction of CO2. And as CO2 as one of the key greenhouse gases that act as a blanket around the Earth, that will result in essentially a runaway effect of cooling down. So it's almost like you're sleeping at night. If the Earth suddenly reduces the amount of CO2 radically, it's like someone just pulled a blanket from you. And suddenly all that heat that you've been radiating is now escaping out and you're left cold. But the inverse of that, if suddenly a mountain out there or a volcano, as it was just migrating up to the surface, intercepted a massive deposit of coal and suddenly ignited all of that coal, all of that can suddenly result in all that CO2 being expelled out and resulting in a huge amount of greenhouse gas on the surface of the Earth, and that blocks all the radiation from leaving the Earth. That you can imagine someone just simply lighting up a nice what do you call a warm blanket, and then piling up more and more blankets on top of course, most of the heat will not escape and you'll become warmer and warmer and you might possibly cook in there. And so ultimately, the key oscillation, you can imagine the Earth's climate is a pendulum that moves from very cold to very warm. And this pendulum has been swinging over time. And for the most part, so looking at our history from about 4.6 billion years all the way to about 500 million years ago, this history is a little bit vague, partly because that history is a bit too distant, but also it's a history which wasn't inundated with life. And life is a very critical component in us being able to look back in history. But over and above, as you can see with this graph, there is a general trend of the temperature decreasing over time. So the Earth started up as very hot, and over time it started cooling down. But in addition to that, there has been a general cooling down of the Earth, but with relative oscillation of extreme cooling down and then the temperature increasing again. And these have been relative glaciation events. So the Pongola glaciation, the Hurrian glaciation, which is considered to be when the Great Snowball effect happened. And all of these have been as a result of certain events. And at the core of it, or the key culprit, has been found to be drastic changes of CO2 in the atmosphere, and in some cases also drastic changes of oxygen in the atmosphere. But a more colorful picture is actually painted in the past 500 million years. And the reason why we have a more colorful picture in the past 500 years is because, well, of our ancestors, all the ancestors who've lived. Life emerged around 3.5 billion years on our planet, but really took off in the last 500 years, becoming more sophisticated and diversifying into different environmental niches. And suddenly it allowed us to have a much more clear picture of what happened, thanks to preserved fossils over time. And this beautiful tapestry has allowed us to glean much better with a relative higher resolution as to what could have happened. And most specifically because marine life is one of the key methods we use to try and track how the temperature has changed. And amongst other things, of course, like what happened to this species, why did it disappear, why did the species evolve, etc., etc. And so the different parts of our of our history, and especially our climate change history, that have been truncated by this event. So first one being marine life diversified, even under extreme heat environments. So you can imagine deep sea temperatures reaching over 30 degrees Celsius. Even in hot environments, life could flourish in parts of the ocean, and generally temperatures, or global average temperatures, ocean and the atmosphere, were around 32 degrees Celsius, which is really hot. Suddenly, we had carbon dioxide, land-based plants suddenly emerged on the surface of the Earth and started eating up all this carbon dioxide in the atmosphere, and that plunged the Earth into a deep freeze environment. And first time we had polar ice caps emerging in our history. And all of that was suddenly the emergence of life and them taking up some CO2 at the same time. Volcanoes eruption, that resulted into a swing of CO2, volcanoes emerging, and also erosion of erosion being much more aggressive can also cause the temperature to swing up and down. Mammals evolved around this time, and this was after dinosaurs were eradicated. And during this time, the Earth also experienced unprecedented levels of warmness, so much so that we find fossils in both on the polar parts of the world that, which preserve forests, and as it were, you can imagine an entire Amazon existed where the North Pole is today. Today, we can't imagine that, but there was a time where you had that. It was so warm. We also had radically warm environments that even our oceans were almost near, it was almost like a hot shower. You would basically find some of our water, oceans or what do you call it, lakes being that hot because the temperatures were relatively hot. But then generally in the last 50 million years, we've had a decrease in temperatures all the way down towards about 18,000 years ago, where we had a massive emergence of our polar ice cap and north and south, and many reasons attributed to that. And we essentially, as human beings, after emerging at around about, well, really evolving around about 4 million years, we then obviously experienced cold spells, and then of course we've had the ups and downs all the way to having mammoths roaming most of the North Pole, and essentially everything being shrouded mostly by ice. But that ice cap has been receding and exceeding over time. So the Earth is a dynamic system. It's been changing for all of this. But one of the key, of all the variables that exist, CO2 is by far the most fascinating variable of all. The Earth's movement around the sun, of course, is a key aspect. Can move closer and further, and that can suddenly cause warming, the so-called Milankovitch cycles. The degassing of CO2 from volcanoes or the plate tectonics, supercontinents forming, that can also change the environment. But the one variable that is just very fascinating, and if you superimpose it with many of the radical changes in our climate, CO2, or more specifically greenhouse gases, but CO2 being one of the most particular of the greenhouse gases, has been one of the culprits that has changed over time. And paleontologists who've looked at fossils, various fossils, and in this radical study over here, they've looked at the stomata of fossils, and they show that the change in the different stomatas will indicate or correlate with radical changes in CO2 concentration in the atmosphere. And that has been correlated, if you look at the previous graph, to relatively the change in temperature. And that is why everyone is obsessed with the idea of CO2 increasing. Now, of course, a lot of scientists may argue that the direct causal link between the of CO2 is not necessarily always very clear and tenuous, but the key thing is CO2 has the power to force our Earth's climate to essentially radically change. Just as I've given you the example, you can imagine as you having one blanket or a sheet that is less CO2 in the atmosphere, to having tons of blankets on top of you, to basically having a lot of CO2. So you can correlate that image to that. So if you have no blanket at all, it's very cold, the Earth tends to be cooler. Then suddenly if you have lots of blankets on top of you, suddenly the Earth is very warm. And CO2 has that effect. And as a result, obsessing over CO2 for most climate scientists has been one of the key things that they've been looking at. And the numbers are startling. Since the industrial age, the amount of CO2 has been rising drastically. And this has caused great alarm. And there is a direct observed correlation to the change and warming of our climate. Of course, our Earth is not necessarily warming across the board. There are parts of the Earth that are relatively seeing some cooler times and more monsoon or more rainfall, but that is the dynamicness of our climate system, that some parts will become cooler while other parts become colder, other parts become more wet, other parts become drier. But the net effect is that over and above, our Earth is becoming warmer. And we are slowly emerging, if you imagine that previous graph, we are slowly returning back into higher temperatures, or going all the way from an average about 13 degrees Celsius, climbing and slowly climbing. And so we will probably see a net increase of possibly of up to 6 degrees Celsius from current or pre-industrial temperatures. So, and last year was considered to be the second warmest year on record, which was relatively about 1.15 degrees Celsius above pre-industrial age. And these numbers while it may seem trivial, are quite critical. Projections by scientists say that our temperatures are most likely to increase significantly if we currently continue at the current consumption of CO2 and production of CO2 in the atmosphere. We will see a net 1.5 degrees Celsius increase all the way by 2040, if we obviously continue with our current trajectory of CO2 emissions. So it is critical for us to either stop producing CO2 or reduce it significantly, or face a possible future where temperatures increase significantly. And that future, it may seem very trivial to most, but is one that ultimately means that we will see a net effect of rising sea levels and a net effect of a dying out of a number of species that depend on certain temperatures to remain. In fact, our extinction rate is accelerating, as it were. You can Google all of this if you want. In addition to that, we will see radical change in our climate. And this is the key aspect. It's not so much that climate is changing, we should worry. The climate will change for as long as the Earth rotates around the sun. The core issue here is the radical change in climate. And this is what I would like to put on the table as a new sort of semantic or term, which is the radical or drastic change in the climate. And that for us, and this is a key thing, is that it can be a short-term effect, but in geological terms, short-term is 100 to 200 years or 300 years or 400 years or 1,000 years. That's relatively short-term in geological terms. But for human terms, that is not a short-term thing to experience. 1,000 years possibility. I mean, the average change in the previous glacial age was been 4,000 years to 2,000 years. That's a lot of time. And that could drastically change our society. A small bug literally caused the entire Earth to shut down. And this has just happened in a matter of a few months. And suddenly our entire way of life has been upended. 1,000 years of radical change in our climate, we can't even predict what that will mean for all of us. And this is where we come to the third theme, which is why it is important to consider negative emissions as another tool to basically try as much as possible to avert this possible crisis. So some clever scientists sat down with specific models to try and see what are the possible scenarios that we could face should we choose a specific path. It's almost like you're sitting on a crossroads, you have to choose which path. You can imagine these are the different pathways that we could have. If we choose to continue on the current trajectory, I hope my color blindness doesn't come through now, so which is the orange graph, we will possibly see a 4 to 4.8, and some people say 6 degrees temperature increase if we don't do anything. So we continue business as usual, we don't bother with anything, which is currently what is happening. That's the possible future we're facing. But if we take a radical stance of trying to reduce CO2 emissions so that we curtail and limit the amount of temperature rise to 1.5, it would mean we would drastically need to reduce the amount of CO2 emissions by the turn of the century. And so these are so-called integrated assessment models. They essentially look at the key concentration pathways that we can imagine that we could have. So starting from our RCP 2.6 is considered to be the most ideal. So essentially these are the different concentration pathways that we could take. And the most ideal of them is RCP 2.6, which suggests that if we can limit our temperature rise to 1.5 by 2,100 years, this would be a more hospitable environment for us to live in and for us to carry on with how we understand life. For some people to still have their vacation home in Cape Town, right at the edge of the ocean, and they can continue doing all the things that they enjoy doing. But that would mean that we have to almost bring down, entirely bring down our carbon emissions to zero. Currently, we produce about 36 billion tons of CO2 per annum. And so over the next 80 years, that's how much time we have, as it were, to basically turn the ship around. So where does all of this CO2 come from? Well, it comes from you and me right now, having your heater on, me having this conversation through this virtual lecture room is powered by electricity. And this is one of the core, has been historically one of the core contributors, because most of our electrical generation is based on fossil fuel, most specifically to South Africa. It's changing in some parts of the world. The diversification in terms of the energy mix is increasingly changing. More people are using renewable energy sources, and that's a fantastic thing, and that will radically reduce the amount of CO2. But unfortunately, you and I are still addicted to that burger. We are still addicted to that wors that we braai every now and then. And we are addicted to that mealie meal. We are addicted to all of these other novelties that we've gotten used to that are thanks to our agricultural revolution. And this obviously means that we deforest or remove forests, massive forests, to make way for all of these places where we're going to put our cows and sheep and all sorts of different animals that end up on our plate. And it's not just them eating up the food and farting out some greenhouse gases, because that's also a very key contributor, but it's that they also destroy one of the key reservoirs of where CO2 is generally stored for a relatively short period of time, or short term, which is stored in all these plants. You know, a tree that can live a good 1,000 years is, you can imagine, a tree that is essentially storing all that CO2. Other parts are all the way from buildings, industrial processes, and of course, transportation. Hopefully, thanks to Tesla, or Tesla run by Elon Musk, that might change with the transportation industry is entirely revolutionized. So the picture is relatively grim, because ultimately, another source, other than just turning away and reducing the amount of CO2, part of what these guys have modeled into these various, what we call representative concentration pathways, is that we've modeled the ability to sequester CO2. And the idea is to store CO2 and remove it from the atmosphere is one of the fastest way we can try and change the ship around. And one of the two ways this is done is either by enhancing the existing natural processes of natural removing carbon dioxide, so encouraging more plants to grow and planting more trees, etc., or making sure that the places where CO2 is naturally stored is very much protected and alive. And actually the ocean, ironically, is one of the most powerful engines that suck up the CO2. But the warmer it gets, the ocean is incapable of storing that CO2. And finally, the second part would be for us to capture that CO2, trap it, use it, either to make our fizzy drinks, but that's a relatively short-term method of doing it, or we can trap it and put it underground, and that's another way of isolating it, or produce other minerals that store CO2 in a more long-term stable manner. So the two methods, bioenergy and carbon capture and storage, those are the two methods that I imagine. And afforestation, that means we encourage forests to grow. Forestation, obviously, this is one of the most easiest and most simplest, straightforward way for us to store CO2. If we could live as minimal as possible, have less of a footprint of our environment, not stop destroying a single tree, not cut down a single tree from today onwards, and in fact grow more trees, this would be by far the most efficient and effective way for us to reduce the amount of CO2 production in the atmosphere. Unfortunately, we are addicted to meat. Unfortunately, we're addicted to cell phones and all these various technologies, which are essentially resultant of all of this, which are destructive and ultimately not conducive to an environment where we can grow trees efficiently or effectively. So we are left with less efficient ways, but slightly more possible ways, which is storing CO2 by capturing it, utilizing it, and trying to store it in a short term, or capturing it and storing it in a long-term basis by trapping it in minerals. And this is considered to be classically carbon capture storage, and it is endorsed by the International Climate Change Intergovernmental Panel. And so a lot of research has been around this, but unfortunately, it's lagging behind. So far, of all of the CCS facilities that exist, all of them have a maximum capacity of about 400 tons, 400,000 tons of CO2 storage capacity. We are producing about 36 36 billion tons of CO2 every year. This isn't but a drop in the ocean. And so right now, most of these systems or facilities exist in the US, or the UK, and partly Europe, in Saudi Arabia, Brazil, but one in South Africa, but it's in infancy. But of the 17 capture sites, and the one component of this that is really thriving is the site where we capture the CO2. The storage component is really lagging behind. The capture part, there are plants that have been really produced in the world that are able to basically capture all that CO2, trap it, concentrated in all different forms, all the way from gaseous to solid state. And one of the most groundbreaking events that happened in 2017, we had one of the first companies that literally sucks up air from the atmosphere, traps the CO2, and we can then obviously utilize it in many different industries, feed it back into the beverage industry, feed it into all sorts of other industries. But the storage side is lagging significantly. And unfortunately, we don't have time. And I know I'm sounding very alarmist right now, but that's a fact. If we consider this graph, that even with, the fact of the matter is we haven't changed our ways. We're still very much addicted to fossil fuels. And with every projection in mind, it seems we are likely not to meet most of our targets. In fact, most of the targets that a lot of those people who signed the Paris Agreement, some of which have fallen out, and key members obviously being the US, most of them are not meeting their targets. And of course, not saying anything about the developing nations. And so in the best case scenario for carbon capture storage, the best would be for us to store about 1,000 to 1,600 gigatons by the turn of the century. That's the best possibility, but that's still relative to the amount of CO2 we produce a year, and assuming we continue that trajectory, it's absolutely nothing. And so the most likely scenario that we are probably facing is RCP 8.5, and that's almost right now an undeniable fact. So if you, for example, look at, so I put on the screen right now, it's this website that calculates the amount of time we have left, as it were, based on certain trajectories. So right now, based on our current production of CO2, we have about 12 years and 3 months to essentially reach and breach the 1.5 degrees Celsius barrier. So that means we will basically increase the temperature by 1 to 1.5 degrees Celsius if we continue with our current trajectory. If we decide to change our ways and everyone meets their target, we'll just add about 3 more months to this entire, the amount of time left before we reach 1.5 degrees Celsius. If by some miracle, I think I prefer this one, we, for example, go to zero emissions by 2040, we actually have no time left anymore. If we were to want to reach zero emissions by 2040, we no longer have any time to do that. If we wanted to reach zero emissions by 2050, we have about 19 months to do so. And after that, time's up. So this is literally a real-time measure of the current scenario. We have 12 years for 1.5 degrees Celsius for us to reach. And then after that, we no longer have that gap. So we now have to go back to essentially trying to now target RCP 4.5, because RCP 2.6 is possibly out of the picture. And as time goes by, and if we don't meet certain targets, RCP 6. And if we don't meet targets, well, unfortunately, RCP 8.5. And that spells about over 1,000 degrees Celsius, 1,000 parts per million of CO2 that will be pumped into the atmosphere by that time, or the amount of CO2 that will be in the atmosphere by around that time. So the question is, what should we do? And what are the possible things that we can do to avert this crisis? And I sound like an alarmist, but to be honest, I don't think we can do anything right now, considering that it takes so much for us to take care of our own health when we are facing a crisis. Putting on a mask is considered to be debt trap by some people. I can't imagine telling people to put away their big cars, tell people to not eat meat as much as often, or for that matter, entirely give it up, tell people to drastically, and of course the economic implications, because that will mean we'll have to shift our economic systems entirely. By all measures and projections, and looking also at sociology, what it tells us about human behavior and how we're able to change behaviors. Most of us can't commit to going to the gym for our own health's sake, when the evidence is there and we know the facts that, you need to eat healthier and you will live longer. We do not change our habits. And if you tell people that, well, most of what you're doing is actually for 2 or 1 generation ahead, whoo, shame, they won't even care. So the likely odds, in my opinion, very alarmist. I think we will get to that point of having our temperature increase to that to 5.4 degrees Celsius. But I think we would have to have a radical approach. And that radical approach involves Mars, Elon Musk, quantum computing, a little bit of solar energy, and finally, carbon capture, and most specifically, geologically induced carbon capture. So, Mars, Elon Musk, quantum computing, a bit of solar energy, and some geological sciences, and hopefully we can radically change our fate. Because it turns out that as much as CO2 has fluctuated over time, that should already be a clue that if we have any chance of, averting disaster or reversing disaster, we would have to undo this effect, and we would have to deliberately sequester CO2 from the atmosphere, and thus reverse the amount of CO2 concentration, which will then have a cascading effect of essentially lowering temperatures, possibly. But that will require a lot of energy, which we can get if we withdraw from this from solar energy, because assuming that by then solar energy technology would be advanced. And quantum computing, it would require radical modeling and calculations of always estimating how much CO2 we can put back in the atmosphere and how will the Earth respond to this. And the type of computing we need for this is, unfortunately, at the moment cannot be achieved. But with quantum computing, we can quadruple the amount of processing power. We can almost move from predicting the weather to there's a 60% chance of rain. But if you can imagine each and every household measuring CO2 levels, temperature, and everything, and feeding that through a massive, powerful network, and feeding that into a massive network which predicts changes in climate, it would mean we will move from predicting by what chance you will have rain, by how much rain, when will it happen. That's what it would mean for us to do that. And so we will need to move far ahead technologically. And we need to be daring, like Elon Musk, and actually dare to imagine ideas that seem radical at the moment. And also borrowing from Elon Musk, if we're imagining terraforming Mars and in geoengineering Mars so that we can make it habitable one day, this is actually existing literature. People want to colonize Mars. It means that we can also geoengineer our world, as it were, towards a more sustainable place to live. Because not all of us will go to Mars, nor is it possible. I mean, if we could get to the technology of terraforming Mars, we should have the technology to also terraform our own planet and return it back to where it is. This Earth has been able to survive from literally 98% extinction of animals. It is possible for things to return back to normal. And this is what we're proposing at the University of Pretoria and my colleagues from Southampton and UWC. We are proposing that we start thinking about using some of this tailings and waste material to essentially store and reduce the amount of CO2 in the atmosphere. And we're currently doing that research. We've cataloged all the mines that have specific tailings that are more likely to be susceptible to be interactive with CO2 such that we can store CO2. But of course, we don't have the technology, but we are researching and looking at possibly using all of this waste material to one day store CO2 and possibly reverse the effects that we've had because we've got all this waste material that's sitting out there. And this is actually natural process of CO2 sequestration. The Earth has always stored most of its CO2 using rocks. So the idea is simple. Take up all that waste material, process it, extract the things that we need, using the energy from solar energy, using obviously technology that is sophisticated enough at that time, and try and find ways of storing that CO2 and reversing the effects that we've done to the Earth, and obviously reversing the time and reversing the CO2 clock, and finally, hopefully, having the Earth return to a more sustainable, habitable environment. That is a radical approach that we're proposing, and that we think that we should already start thinking about in these radical terms, because I don't think we will change our behavior anytime soon. Thank you. Okay, that's it.
Well, thank you very much, Zakhele, for a very interesting and thought-provoking presentation.
It's a pleasure.
If anybody wishes to ask a question, please raise your hand. Or you can type a question in the chat box as well. We'll get to both of them. Looks like everybody was very worried you were going to ask them to give up Boerewors.
I think so. But luckily, I think they won't.
Sorry,
Murray?
I'll ask a question.
Yeah, please.
Sure.
Yeah, I've been wondering about this for a while now, but it's going to be very difficult to get people to stop building things.
Mm-hmm.
Why can we not use, what do they call it, non-hydraulic cements in the building industry, which actually sequester the carbon automatically? Do you have any thoughts about that?
Well, not necessarily in that specific technology, but we have been, this is precisely one of the core underlying aspects of carbon capture. One of the things that we've been imagining, as it were, is that we could be having an entire supply chain system that looks at all different types of mixtures in this entire system, but the core aspect with that supply chain system is the sequestration of CO2. So having very smart engineered cement that also, I mean, because buildings as they weather actually are part of the entire equation of sequestering CO2, and that's basically one of the reasons that they weather over time, is that there is a natural interaction with the ambient environment around them. So that is already imagined by a lot of guys within the material sciences. I mean, one of my co-supervisor in Germany, he was focused on using cement material or deriving cement material or producing cement material that is derived from part of the CO2 sequestration supply chain. So that's part of the solutions that we can add to the mix.
Yeah, and I would imagine that with a lot of the tailings from the kimberlites, you should have almost readily available access to calcium hydroxide, which is basically what you need for that kind of cement.
Mm. Can you repeat that?
I'm just thinking that if you have access to kimberlite tailings, I would imagine that there should be quite a bit of calcium hydroxide in the mix somewhere, and it's that calcium hydroxide that allows for the non-hydraulic cements to work.
Oh, there's a lot of it in kimberlites. I mean, that's part of what the guys in De Beers also discovered, and also the guys in Canada realized that, oh, there is a lot of brucites that's sitting around in these kimberlites, and it is sitting in the bucket loads, and this is one of the core ingredients that you could use. So 100%, yeah.
Thank you. We have Murray, who's got his hand up. Would you like to unmute yourself and ask your question, please?
Thank you, Tanya. Hi, Zach. Great talk.
Hi, thanks.
I just want to know, this might be a dumb question. I'm getting well known for those, but how do you capture carbon from the atmosphere to sequester it?
So Celia's, that technology is actually far more advanced. In the entire carbon capture, I would say, process chain, the capture component is highly developed. It's more in the chemical engineering side. So all the way from having these sophisticated, I forgot the actual term, but you have these, you create sometimes these sophisticated crystal lattices that are able, sort of like where you pass the gas through and it's able to just essentially trap the gas. And a lot of, what do you call these places? Electricity generating spaces that still use, obviously, thermal generation of energy have retrofitted some of these sort of, I would define them very roughly as like scrubbers or, gas flue scrubbers that basically trap the CO2 and essentially concentrate it. So, and that's slightly in the realm of engineering, and chemistry, so it does fall outside of my scope of understanding, but there is already a well-developed pool of tested technology and implementable technology. Hence, right now we are capable to have commercial scale sort of like factories that are able to suck up air from the atmosphere. So it's not just, oh, you're burning coal, you happen to be producing CO2 that happens to be concentrated and you're preventing it from being stored in the atmosphere. We can actually suck up the air as it stands and basically concentrate all that CO2. The only issue in the process is that, yeah, sure, the utilization of it can be found somewhere along various industries, but ultimately, because there's so much CO2 in the atmosphere, I mean, 400 parts per million CO2 concentration is nip up in place. And so all of that would end up having to be concentrated or stored safely somewhere. So this is the other problem in the entire chain, as it were. I see Patrick is asking another question. Celeste, is that okay? Does that answer your question? I can answer Patrick Richards' question.
Yeah, thanks, Zach.
Cool. So he's asking, are there specific tailings for certain commodities that are more suited for carbon storage? Yes, this is at the core of my research and my colleagues from Southampton and UWC. So we've identified all the commodities that are associated with ultramafic or ultramafic to mafic rocks are generally the ones that carry, as pointed out by Ego, the calciums and magnesiums, and maybe iron, but mostly calcium and magnesium that can then be bonded through certain chemical processes to form stable carbonates. So naturally, and this is an interesting component, is that naturally the Earth does this, but it does it over thousands of years. The Earth, if you look at all the limestone that's sitting around Centurion and all these places, that is CO2 that used to be in the atmosphere. So if you're walking around Centurion, or hopefully not in a sinkhole, and you're seeing all this dolomite and limestone sitting around, that used to be CO2 in the atmosphere. And the Earth, through its own geoengineering processes, has stored that and has isolated it from the atmosphere. And easily, as it weathers away, because of the current events that we're having, that as CO2 is also liberated and sent back to the atmosphere. And so that's also the other danger, is that the feedback loop that is happening is that as we have more CO2 in the atmosphere, we're having far more corrosive environments, which result in accelerated weathering processes, which can in some cases liberate or make the ocean more acidic or dam waters acidic, which can then result in some of those dolomites which have stored CO2 to actually release the CO2, and that can cause a negative feedback loop or a positive feedback loop, actually, which then accelerates the whole climate change chain of actions.
Do we have any more questions? Oh, sorry, Zakhele, you weren't finished.
No. I'm finished.
Any other questions? Comments? Going once? Going twice? Sold. Zakhele, thank you once again very much for the presentation. And at this stage, I'd also like to thank TerraCore, who is this month's sponsor of the GSSA Lunchtime Lectures. Well, thank you all for coming, and we certainly hope to see you again soon. I just see there are 2 chats coming up. People who are just showing their appreciation for your talk, Zakhele.
Thank you so much.
There are more lunchtime lectures coming up. Please check your calendar, and we hope to see you again soon. Thank you all.
Thank you so much.
Thanks,
you everyone for
Zakhele.
attending.
Thank you so much.
Thank you.
Thanks, ciao.
Bye.